This video is for Chapter 6, Section 3. It's all about the ways that we can prove a quadrilateral is a parallelogram. This video is meant to go immediately after Chapter 6, Section 2, almost to where you would want to watch them back to back. Because all the things that we learned in Chapter 6, Section 2, the properties of parallelograms, we're going to find out now if they go backwards. The last lesson started with, it's a parallelogram, what do we now know? We're going to go to the reverse of that and say, look at what I know. Is that enough to prove it's a parallelogram? So we should first start with the thumb, which in the previous video was by definition. So, can you prove a parallelogram by definition? Sure. We can say that if both pairs of opposite sides are congruent, then it is a parallelogram by definition. Previous lesson, if it's a parallelogram, that means both pairs of opposite sides are parallel. Today's lesson, if both pairs of opposite sides are parallel, conclusion, it's a parallelogram. So, the reverse, this is the converse of the previous lesson. If the sides are parallel, then it's a parallelogram. This goes on the thumb, because in the last lesson the thumb was the definition, now we're proving by definition. So let's start taking a look at the properties and see if we can put together the other 4 ways to prove something is a parallelogram. So, number 1, if both pairs of opposite sides are congruent, then it's a parallelogram. So we start off with, this is just a quadrilateral. We have not been told that it's a parallelogram. What we've been told is that both pairs of opposite sides are congruent. Our conclusion is, we can say it's a parallelogram. Now, although we're not going to do it, and we'll spend more time in class, this comes from the fact that we could cut this diagonal, and we could say, look, those 2 triangles are congruent by side, side, side. And from the previous lesson we learned that the parallelogram is a shape that can be cut into 2 congruent triangles in this way, such that it causes alternate interior angles and the lines become parallel. So, we have evidence that if we start with both pairs of opposite sides congruent, then it is a parallelogram. Alright, so there's 1. We had by definition, and now by property 1. We'll go to property number 2. If both pairs of opposite angles of a quadrilateral are congruent, then it's a parallelogram. We have to add the starting markings here. So, if M is congruent to T, and A is congruent to H, then we have enough evidence to suggest that this is a parallelogram. We would probably look into the idea again that these 4 angles have to add up to 360, creating 2 pairs that add up to 360. That means each pair adds up to 180, causing the lines to be parallel. More important for today is, if we have 2 pairs of opposite angles congruent, both pairs, not one pair is not enough. We have to have both pairs. Then we can call it a parallelogram. So if A is congruent to H and M is congruent to T, then MATH is a parallelogram. By definition, if both pairs of opposite sides are congruent, if both pairs of opposite angles congruent. 2 more properties. Okay, here are the last 2 ways that we can prove a parallelogram, and the third one from the previous slide, the first 2, here's the third one. If the diagonals of a quadrilateral bisect each other, then it is a parallelogram. The key idea here is that with these vertical angles, we can see that this top triangle is congruent to this bottom triangle by side angle side. Same with the ones on the sides, side angle side. Now, because these triangles inside are congruent, it produces a bunch of congruent alternate interior angles which cause it to become a parallelogram. We're going to explore this more in class, but for now, if the diagonals bisect each other, then it is a parallelogram. Make sure that it is both diagonals that bisect each other, not just one. You cannot just have those two markings. You must have all four. These bisect, these. As long as both diagonals bisect, then you can conclude parallelogram. And now the fourth and final way. If one pair of opposite sides is both parallel and congruent, this also causes the shape to become a parallelogram. We could divide this into two triangles and prove them congruent. We could look at the idea that if this is 10 and this is 10, that connecting them, as long as they are equal distance away from each other, will cause these sides to also be congruent. So we have parallel and congruent forms a parallelogram. This is the fourth and final way to prove something is a parallelogram. Make sure you understand it's one pair is congruent and parallel. Not this. This is one pair parallel and one pair congruent. That does not prove a parallelogram. That is sometimes a parallelogram, sometimes an isosceles trapezoid. This is a guaranteed parallelogram. One pair parallel and congruent at the same time. So, recap. Prove a parallelogram by definition. Both pairs of opposite sides are parallel. Number one, if both pairs of opposite sides are congruent, then it's a parallelogram. Number two, if both pairs of opposite angles are congruent, then it's a parallelogram. There has to be both pairs. Number three, if the diagonals bisect each other, both diagonals, then it's a parallelogram. And four, if one pair of opposite sides is both parallel and congruent, then it is a parallelogram. That's the end for Chapter 6, Section 3, How to Prove a Parallelogram.